All right, so looking at our optimization steps, finding the max and min, the optimum situation, and they can vary from fairly easy, straightforward to a lot harder based on getting things set up. But bottom line is this stuff here at the end is our basic steps. Once we have the equation we're trying to maximize or minimize, then it's do the derivative, set it equal to 0. Is the derivative ever undefined? What's happening at the endpoints? And then justify, like list of candidates usually, that it's a max or a min, answer the question. So the key is, getting this thing set up. And we worked a lot on that yesterday with those pictures. So let's look at what we had on 28. This is what you kind of had left on 28. 28 was the cylinders. Okay, and so they had described in there, we were trying to find the maximum volume, and so the volume of a cylinder is pi r squared h, and that has more than one variable, and so we had some other information. The long side is h, the girth is the distance around perpendicular to the long side, so that would be 2 pi r. So the long side plus the girth has to be 108. So we solve for h, we get that. We substitute that in there. We get this, and away we go. We do b prime. We set that equal to 0. What did you get for an r value on 28 there? My answer book's kind of mixed around on that one, but it was 12. The first one here, this one, the taller one. On this one? Okay, yeah, see, I think my answer book is backwards here. Yeah, it's on the other one. Okay, so you end up with 36 over pi as your only stationary point. So you do the derivative, set equal to 0. What's that? And 0, which is one of our endpoints. So the littlest r could be is 0. Of course, you could have no radius. Of course, would be no cylinder, so that's not going to have B volume. And then what's the biggest? The biggest r could be is when h is the littlest, right? It's when h is the littlest. When the biggest r could be, of course, see, that would get into this. So now, and I've had discussions, I've had arguments with other class, not arguments, but, you might say to yourself, well, the biggest r could be is when h is the littlest. Well, actually, when h is the littlest, you have hardly any height. Well, then you start getting into this case, actually, right? I mean, so I would be okay. I probably wouldn't count it against you, though technically it's probably wouldn't be correct here. If you said, well, when h is 0, so that'd be when h is 0, you would have 108 divided by 2 pi, which would be 54 over pi. So I could see you saying that is one of your endpoints. However, when would you go from this case? When would you go from this case and then all of a sudden be into this case? Well, not r is bigger than h. It's the whole diameter that's the long side, right, down here. So as soon as 2r gets to be bigger than h, right? Well, so that would mean that the biggest r could be is when 2r is equal to h, right? Well, then just put a 2r right in here in place of h, right? When 2r is equal to h, okay, then you would have 2 pi r plus 2r equals 108. Take out an r, you'd have 2 pi plus 2. You could go to decimals here. And then you would have r would equal 108 over 2 pi plus 2. Right? That's actually technically the biggest. What is that on the calculator? Do that for me. Just do 2 pi plus 2 as a decimal. Do 2 pi plus 2 as a decimal. Okay, now do 108 divided by that. 13.04. What's 54 divided by pi? 17. So we would be saying here 17 point something would be the biggest. It's actually about that would be the biggest. Okay. So we are now at that there we are getting into the realm of probably a little more in-depth, you know, than I would ask you on the quiz, right? If we're just focused on that, figuring that out. But I mean, let's understand. I mean, right? I mean, it's not beyond our, shouldn't be beyond our capabilities to think that through, right? The biggest R could be, because as R gets bigger, this thing starts to get fatter, and H would start to get smaller, and then pretty soon we're into this case down here. Okay, so to be honest, it should be that probably would be your endpoint. Okay, not that. Okay, so when you do your list of candidates on this, you're talking about V of 0, which of course is going to be 0, V of 36 over pi, okay, which is going to be the one you want, and V of 13.04, whatever, would be your example. So they came up with the volume on that one is at 14,851, I think. If you plug this number, if you plug 36 over pi back into there, okay, you get 14,851, something like that, cubic inches. And then on this one, so then the difference on this one is the long side is now across here. It's 2r, the diameter. So the girth would be perpendicular to that. So that would be 2r here, 2r here, h here, h here. So that's 4r plus 2h would be your girth. And then plus your long side is 2r. So that would be all this. So if you solve that for h, you get that. And so now you substitute that in for your h up here, and you get this. On this one, then you do your derivative, you set it equals 0. Of course, it's never undefined. That's the one you get r equals 12. Okay? And the same thing goes here. Technically, we would have, what's the smallest that r could be here? Well, technically not 0, right? If r is small, then you're in this case up here. So again, it's when 2r is equal to h would be, that's when we would be at our smallest, right? So you could put a 2r right here for this h. So that would make that what? 4r? So it'd be 2r, it'd be 6r, it'd be 10r. 10r equals 108. So r would be 10.8. So the smallest r could be here would be 10.8. That'd be the smallest r could be, because when 2r and h are equal is when you shift from one to the other. So 10.8 would actually be the smallest. And then, but if you put 0 there, I wouldn't count that against you, whatever. Okay, and then what's the biggest r could be? The biggest r could be is if there was no h, and so that'd be 6r equals 108. So what's that? What's 6r equals 108? How much? 18. So that'd be the biggest. So your list of candidates would be, you plug in a 10.8 something, technically you plug in a 12, you plug in an 18. I think when you plug in 18, you don't get any. You get 0. But you do your list of candidates and it happens at 12, it's only like 8,000 something. I think it only comes out about 8,000 if you plug in 12 into that volume. So between the two of those, the max volume is the 14,851, and that would be when your radius is this right here. And then you have to answer the question, did it ask for dimensions or did it say? Find the dimensions, right? Find the dimensions. So that would be radius 36 over pi, and then you would plug that right back into here to get your height. So that would be the radius and the height. So take 36 over pi, plug it back into that. And it works out pretty nice, actually. You have 2 pi times 36 over pi. Pi's cancel, so you get 72. 108 minus 72 is what, 36? The height would be 36, I think. Okay? All right, so that was 28. We had to finish that. Let's go to 27. The 27 talked about surface area. These are kind of some basic, I mean, we need to be able to work with these kind of shapes, right? We need to be able to work with these kind of shapes. They're pretty basic mathematical shapes. It says a piece of wire 100 centimeters long is going to be cut into several pieces used to construct the skeleton of a rectangular base a rectangular box with a square base. What are the dimensions with the largest volume, and what's the largest surface area? So if we're going to do volume, that's again x squared times y. How much wire do we have? We have 100. Well, what do you got? You got x, 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 and x, 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 and x. You got 8x, right? You got 8 pieces that are x long, okay? And then you got 4 pieces that are y long. So your skeleton of this thing is going to need 4 pieces that are y long, and that has to add up to 100. So you divide, so you solve for y, get that, you plug it in there, there's your v. Do your derivative, set it equal to 0, I get those numbers there, 8 1/3, 25 thirds, whatever. Okay, that derivative is never undefined. My endpoints, the smallest it can be, of course, x could be 0, and the biggest it can be is if you don't use y at all, right? If you use all your wire for x, well, that'd be 100 divided by 8. 100 divided by 8 is 12.5. Okay, so the biggest it can be is 12.5. So we do our list counts. Of course, we get 0 for both of those. 25 thirds, whatever that comes out to be, I think this says 578.7 something. Okay, but they want the dimensions. So if x is 25 thirds, you put 25 thirds back into there, and you get 25 thirds. So wow, it ends up being a cube. Well, that's not surprising, actually. Okay, so you put 25 thirds back in for your x up there, you get your y, and you got it. Okay, so there's your dimensions. And you probably want to put the units on there, centimeters. Okay, surface area. What's a surface area? Surface area of a box is just adding up all these surfaces. So what's the area of that front surface right there? X times y. How many of those are there? There's 4 of them, right? There's one on the side here, there's one around back, there's one on that side. So I have 4 that are x, y, okay? And this surface is x times x, x squared. There's one on top and one on the bottom. So I got 2x squared, okay? We got to know what surface area is, right? That's just the area of each of the surfaces. So step 1 is write an equation. Identify what you're trying to maximize, which is surface area. Write an equation for it. And now get it in terms of one variable. Well, we have the same constraint here on our wire, right? We still have 100 centimeters of wire, so it's still that, okay? We still have that, and so we substitute that in for the y, we get that. I went ahead and simplified it out. We do a prime. Oh, look at that, we get 25 thirds again. It's going to be a cube, right? It's going to be, I mean, it's pretty, there's nothing special about this problem, and that's pretty, kind of like we talked about with the square. For a given perimeter, for a given amount of material, the max volume and the largest surface area is going to be a cube. And so we can finish it out, but that's it. I mean, again, 0, littlest x could be a 0, the biggest x could be as 12.5. Those two things aren't going to change in this problem. Okay, we plug those into our area. I think they got 1,250 divided by 3, whatever that is, 416 or something like that, I don't know. Whatever that number came out to be, that's going to be your max. And so your dimensions, again, are going to be just like this. It's going to be a cube. Okay? Pretty straightforward. Let's talk about 19 and 21. This is one of my favorite problems we do. I don't know if it's because I'm a track coach or something, but and I'll show you why that is in a minute. So we go to number 19. So a lot of you didn't have much done on 21, so we need to talk about that. So 19, I just plugged in the numbers they said. If you got 30 is your initial velocity, you're going to kick a football. Here's the ground. Now let's say that the football's on a tee right here, right? We're going to kick it. And we're going to go 30, what was it, meters, feet? What 30 units? Meters per second. So we're going to go 30 meters per second. We're going to kick it at a slope of 1, which is what? In angles, 45 degrees, right? So we're going to kick it at a 45-degree angle, okay? Gravity is 9.8, so we just plug those numbers in, okay? We just plug those numbers in, okay? So that becomes our equation. Of course, 1 plus 1 is 2. We could multiply this out and kind of get a simple. We can see it's a parabola. These are just a bunch of numbers. You get a parabola, upside down parabola. It's going to do that. Put that into your calculator, okay? The question says, how high does it rise? Well, y is your height, and x is your how far it goes. This is kind of related to our parametric equations, except they're not parametric. It's just a y and x equation. Okay, how high does it rise? Isn't that a max? Isn't that the max of y? I mean, so that is a max problem. It is a max problem. But it's also one we could have done before we start talking about max. We just know it's going to be at the peak. It's when the derivative is 0, right? So you do the derivative of that. You set it equals 0. And you ended up with what? Where did that happen? 45.92 something. So you get x equals 45. They don't go out to 3 decimal places here. They're going to say 45.92, but you get the idea. You'd want to do 3 decimal places and so forth. So, but they want to know how high, right? Is that how high? That's the x, right? So that wouldn't be the final answer, right? That's what you get for your x, but what do you got to do with that? You got to go plug it back into there, right? Because the answer to the question is how high did it rise? So that's like 22 something, right? I got 22.96, they say here. So how high was it is the y value, but the x here would be 45.92. Okay. Then it says, where does it land? Well, what do you do for that? Put a 0 right here for y. Right? When does it hit the ground? We did this. We did this when we were doing the parametrics, right? When the y is 0 is when it's back on the ground. Well, to be honest, since we kicked it from the ground, and you know this is a parabola, and a parabola has symmetry, isn't it just going to be double this number? It's going to be double this number, right? It's a parabola. The vertex has to be halfway. So you could argue that, but just put y equals 0, solve it, and you're going to get 0, and you're going to get 91 point, whatever, 84. Something. This is how far out the plan is. Okay? All right. Any questions about that? On 19. Okay? So it's just I don't know if you were intimidated by the look of all those letters or something, but whatever. Plot the trajectory. I probably won't have, because you're using calculators, so you just graph it, right? I mean, that's not a big deal. Okay, but here's 21. 21 I really like, because what they said is, in 21, in the situation in 19, the projectile has a range. The range is a horizontal distance covered before landing. Now, didn't we just do that in this problem? Didn't we just do the horizontal distance where it landed? And what variable was that? That's x, right? X is the horizontal distance. So in their problem in 21, what did they call it? What did they call it in 21? In that equation they wrote. What they call the horizontal distance? Huh? R. Right? They just renamed it. They said, let's let R be the range, the horizontal distance it covers for landing. Well, that's just x. That's just x in this equation. So in part A, they say use the formula in exercise 19, which is this one, to show why the range formula holds. So what did they do in this problem? To get R equals, what did they do to this? Well, they just solved it for x. That's all they did, right? R is the horizontal distance it travels. Well, that's what x is in this equation. So all they did was solve this for x by putting a what where? Well, they put an R in for x and what in for y? 0, because they want to know R is where it lands, and that's what we just got to say. To find out where it lands, you put a 0 in for the y, because that's when it's on the ground, and then you solve for x. But they call it then R. So all we're going to do is we're going to put a 0 right here, and we're going to solve this for x. Okay, so that's going to be part A. Okay, so how am I going to, now notice I put all these letters back in because we're going to do a different scenario here. Okay, so I put G back in, B sub 0, whatever. So what would you do? What do you think you would do to start solving this for x? Now remember, M and G and V are just numbers. So basically what you have here is AX minus BX squared equals 0. That's basically what you have. This is, call that A. I call all of this mess B, because this is just a bunch of numbers. What would you do to solve this? What would you do to this right here? What would you do to this to solve this? think you would add this over. You would factor out an x. And then what would you do? Set each one equal to 0. That's what you should do. You don't want to add this over, because then you end up dividing by x, and that's bad. You don't want to divide by x, okay, because you might be dividing by 0. So we want to factor out an x. So, oh, I divided over. I added it over. Well, okay, let me show you one. It does end up being the same thing. As soon as I said that to you, I thought, well, you could, as long as you thought that. But the problem is most people don't think of it, okay? I did it because it's not quite as basic. If you divide by x, what's the problem? You don't want to divide by 0, right? Well, let's think about this problem. When in this problem is x 0? At the beginning. So is it okay if we eliminate that part anyway? We don't care about that, right? What we care about is this x over here, right? So all we're doing is eliminating the start. So in this case, dividing by x is going to be okay. All right, but as a general rule, I wouldn't want to do that. So so I'm only going to do this because that's how I set this up. So I did. I added this whole big mess over here. So now I'm going to divide by x. Okay? So I'm going to divide by x, divide by x. Okay? Now what? Now I got just this x. Now I got to get the rest of this over here, right? Let me see what I did next. Okay. So I'm going to take this and I'm going to divide this over first. So I'm going to have m over 1 plus m squared. With me? So I'm going to have m over 1 plus m squared on this side. And so now this is gone. And so I got my x, and then I got this fraction. And now how can I get this fraction over there? Flip it. So I'm just going to flip it, and there we go. And I think that's what they have on number 21, except now that x is called off. Right? There you go. Okay, so it's not magic. It's just some algebra. Right? It's just some algebra, but it's kind of messy with all those letters, and it freaks people out. Okay? But that's what it is right there. Okay? Now, here's the gist of this problem. Here's the real interesting part of this problem. Suppose that v sub 0 is fixed, but m is variable. What value of m maximizes the range? So in our previous problem, we did a 45-degree angle. We kicked it out. So we let m be 1. Our initial velocity, that's just going to be a fixed number, right? And gravity, of course, is fixed, 9.8. So what we're saying in here, in this problem, is we want to maximize range. So let's say you're a kicker in football. Don't you want to kick it as far as possible, probably? Right? So what we're trying to do is tell them what? We're saying, let's let m be our variable. That's our slope. Right? But we're going to kick it always with the same initial velocity, because same guys kick it. So he kicks it, he's got the same lane strength every time. Now sometimes you might kick a little harder. Let's just say you kick it the same velocity every time. But we're going to vary m. So what's that mean? We're going to vary what? The angle that we kick it at. So what we're trying to find is what angle should we kick it at to make it go the farthest? Should we kick it up high? Well, geez, what happens if you kick it too high? Doesn't go very far. What happens if you kick it too low? It hits the ground. It doesn't go up high enough. It hits the ground. Right? There's somewhere in there it's probably the best angle to kick it at. Right? Now I always use this example as a track coach. I think of a shot put. Right? I think of a shot put. Right? So this is the formula to tell how far this thing's going to go. Now, the difference is a shot put deal throw from the ground. It's up here, so that changes things a little bit. But the angle you throw it at is one of the factors. Now, what's the other factor? Of course, gravity you can't change. What's the other factor? Your velocity, how hard you throw, right? So as a shot putter, you can control those two things. You can control how hard you throw it, and you can control the angle you throw it at, right? So we're just going to say, let's say this is fixed, okay? Velocity, you're going to throw it the same every time, okay? Velocity. What is our max? So that is the problem we want to do, okay? So I've got R right here. I went ahead and did R prime, which remember, this is just a number. This is just a constant, so it's just going to hang out there. I went ahead and did a product rule. M is my variable, so we're doing dr dm. We're doing the derivative with respect to m, okay? So, derivative top is 1. derivative top is 1 times the bottom left alone, so that's 1 plus m squared, minus the top left alone m times the derivative bottom is 2m, all over the bottom squared. So I go ahead and I mess with this. This would be 1 plus m squared minus 2m squared, so that'd be 1 minus m squared. The bottom is just 1 plus m squared squared, and that's r prime. I want to know where that equals 0. Well, this is just a fraction. This is just a number, so we just forget it. Here we only care about when a fraction equals 0, it's what? When the top is 0. Is the bottom ever going to be 0? Is this ever going to be undefined? Everything's squared down there, right? M is squared plus 1, then you square it. That's all positive. That'll never be 0. This will never be 0 down there. Okay, so r prime's never undefined, so I got that. Okay, so 1 minus m squared equals 0. M is plus or minus 1. Well, we're certainly not going to kick it down, right? We're not going to throw it down. Okay, so m equals 1. So, don't you think? Now, do we have any endpoints? Well, I suppose, what's the littlest m can be? 0. Well, you throw it, obviously that's no good. Okay, but that would be, what's the biggest m can be? Well, now 90 degrees, but we're talking m here. M is slope. That'd be undefined. Wouldn't that be infinity? That'd be infinity. I mean, that's what a slope is, right? That's why it's undefined, because it's infinity, right? So basically infinity. Okay. Well, let's look at this. If you put a 0 into here, so now we want to do r of 0, right? Well, if we do r of 0, we're going to have 1 over 1. So we're going to have whatever that number is. Okay. Well, that seems weird that it's going to not be 0, but it might be. Oh no, I got to put it into here. No. Why am I putting it in here? I got to put it into r. So I come up here to r and I put in 0. Yeah, sure enough, put in 0. Just 0. Okay. I put in, as m goes to infinity, what's happened to this as m goes to infinity? This is going to 0 because the bottom's getting really big, right? Bottom's getting really big, so that equals 0. And so then we do r of 1. So we put a 1 in here, right? 1, that's what? 1 over 2. So the 2's are canceled, so that'd be v sub 0 squared over g. Well, that's clearly bigger than 0, right? That's my max. Okay, so that's clearly my max. So you should kick that football at 45 degrees. 45 degrees, so there you go. We just proved it. That it makes sense. So in track, a long jumper leaves the ground and wants to get out the farthest. What should be their takeoff at? 45 degrees. One of the hardest classes I took in college, I'm a math major now, remember? The hardest class I took in college was a coaching class. I took a 1 credit hour coaching class. It was biomechanics of coaching. It was basically kinesiology, which is the movement of the body and stuff like that, the study of movement of the body, stuff like that. It was 1 hour, it was biomechanics of coaching. And that's what we studied. There's a lot of physics and stuff like that. We talked about throwing the discus and jumping and kicking a football and all that stuff and all this math and stuff. Jeez, it was hard. Hardest class I took, 1 hour for coaching, which you don't even need to be coached. But anyway, so I was like, why am I taking this? But anyway, thought it would look good. But that's the kind of stuff we did. Not as a math guy, so I didn't mind it, but it was still hard. A lot of stuff. So, 45 degrees. Now, this is interesting. I don't think I have any shot putters in here, but Emily could have been a good one, but she chose soccer. But when I've had people in class who throw the shot put, I asked them what Coach Larson would tell them to throw the shot put. And they would always tell me about 42. He didn't, they said, first of all, he didn't talk about it a whole lot, but a few of them that kind of paid attention said like 42, 43 degrees is what he told me. Why do you suppose that is? No, not with a shot put. I don't think the wind's going to bother the shot put. Discus, the wind is an issue. So there's a lot of issues there. But why do you think that is? Where do you release the shot put? You're not starting at the ground. So if the optimum trajectory of a projectile is a parabolic path, but you release it here and then it hits the ground here, the 45 is back here, right? What's this angle right here? Less than 45, right? Less than 45. The slope is decreasing, right? Depends on how tall they are, right? A taller person would throw it, what? A little lower angle. The taller you are, a little lower. The shorter you are, a little more towards 45. Now, here's the real key. Here's why most of those shot putters didn't know that. And here's why Coach Larson, when I talked about it, he knew this. He knew that it was around 42. But I talked to him about the math. This was years ago. I talked to him about the math. He thought it was interesting. But in the equation, we said there are two factors that affect how far it's going. There's the angle you throw it at, and there's what else? There's velocity. Which one of those two impacts it the most? Probably this velocity, right? So if you had a shot putter you were coaching and you wanted them to really improve, right, you're probably going to focus on weight room, technique, right? Some guys spin when they throw the shot put to get more force and get more velocity on there, and so getting their hips under them and balance and all those things affect how much force you put into them. Those all are fixable and you can improve on. So they spend a lot more time improving this than that angle. But if you got to the Olympic level, the elite level, the top 2 or 3 where inches would separate them, right? That's where that video analysis, all that comes in. They look at it and they say, you can improve that angle just a little bit, right? And they could, so then they might really focus on it. So it might become an issue. Okay? You guys have seen that on ESPN, that Sports Science or whatever those shows, where they look at all that different stuff, right? I mean, this would be in the realm of that kind of stuff. Okay, let's talk about the business packet real quick. These problems, let me see. Okay, so on 3, so it says find the number of units X that produces a max revenue. Okay, so we're already on step 4. So if you were struggling with this, you were making it way too hard. The max revenue, they give me the revenue equation, so I just need the max amount. So I just need R prime equals 400 minus 2x. Set that equal to 0. 2x equals 400. X equals 200. They don't give me any endpoints. I could argue it's an upside down parabola, so it's got to be the max, right? It's got to be 200. You could do a number line. That would be not bad either. A number line would be really quick. You could just say, hey, they didn't tell me any information about it, so I don't really know my endpoints. So you could just say, okay, R prime, put a 200 on it. Okay, what do you get if you put 100 into here? You get 400 minus 200. That's positive. What if I put 300 into here? You get 400 minus 600. That's negative. Okay, there you go. And then you give your rationale. Now, I've been shortcutting this because for time. I'm not going to write this out every time. You guys got to know that's how you do that. You got to show your justification. So you'd say R prime is always positive before and always negative after. So R is always increasing before and always increasing after. And so that's why this is a max. So that's the number of units. So Max, does that make sense? I mean, you were saying you never really understand that. Oh, you got that. Okay. All right. So then this one. Okay. Now this next one you need to calculate. So find the number of units that produce the minimum average cost per unit. Now what did we say C bar was? C divided by X. So C bar is simply this equation, 0.02x cubed plus 55x squared plus 1250 divided by X. It's just that. So you just put that in your calculator. And so you get C bar prime, whatever that is, right? You set it equal to 0. You see if it's ever undefined. It's probably undefined at 0, okay? But that's not going to give us it's not a number we can even plug into C bar, so that's not going to be a minimum. And so I don't have the answers handy on this one right here. Well, I guess I do. Let me pull them up. I'm going to put these on the website, by the way. So there's C bar. C bar, I simplified it. There's C bar prime, and I got 4.759. I must have got something else and crossed it out. I don't know if it was. And X equals 0 doesn't really work. Now again, I didn't go through and do all of the the justifications on this answer sheet. I just wanted so you could see what the units were, but again, it's kind of a single, it's basically a single candidate. You can do a number line, show that it is a minimum. Okay. All right. So we're gonna keep working on those. We're gonna keep working on these max min kind of situations. But go ahead and get your notes out right now. And we are gonna talk about the last section that this quiz is gonna cover. It's gonna be section 4.5. All right, the title of this topic is related rates. Related rates. And let me see. All right, so we're not gonna write that down just yet, but okay. So related rates. Now we're talking about rates. So we're talking about movement. We're talking about changing quantities, and within a problem they're related. Now we're going to have kind of a recipe of steps, but now this is totally different than optimization. You should not confuse these two because they're just you're accomplishing totally different things. In optimization problems, it's asking you to find a maximum or a minimum or a largest value or a smallest value. Okay? These problems are all going to say things like, how fast is this changing? Okay? At what rate is this changing? So they're all going to be talking about rates. Okay? So it should be very easy to tell the difference between the two of them and how we do them. Okay, so let me do a couple, and I don't know that you need to write any of this down here. It's totally up to you. But we've talked about calculus being the mathematics of change, increasing, decreasing, growing, shrinking, whatever. Changes occur over time. So what we're going to be doing is derivatives with respect to t, to time. So it says write the following statements mathematically. So let's just do this together. So John is growing at a rate of 3 inches per year. Write this mathematically. Well, I would call that J prime. Now, more specifically, and you're going to see me talk a lot about this, is the Leibniz notation, dj over dt. It's a derivative with respect to t. We're going to be doing some implicit differentiation. Okay? You might remember if we had an equation like x squared y equals y squared or something like that, and we were going to do the derivative of that with implicit differentiation, what did we write? Well, first of all, what did we have to do with this? But we had to do the product rule, right? So the derivative of x squared would be 2x, we leave the y alone, plus the x squared left alone. What's the derivative of y? Y prime. Why do we have to do that? Because we're doing the derivative with respect to, derivative with respect to, what are we doing the derivative with respect to? X. We're doing the reason we do that is dy over dx. We're doing the derivative with respect to x. Okay? So why didn't we tack on an x prime? Because that would just be dx over dx, right? So we didn't tack on an x prime because we were doing the derivative with respect to x. And then over here we'd have the derivative of y squared is 2y y prime. We have to tack on a y prime because it's like the derivative inside. It's like the chain derivative of y is y prime. It's dy over dx. Okay, now, with these problems, we're going to be doing the derivative with respect to t every single time. They're all going to involve rates that involve time. My mutual fund is shrinking by 4 cents per day. That would be, let's call M for mutual fund. M prime is equal to 4. Well, it'd actually be negative 4, right? Because it's shrinking. So it would be M prime equals negative 4. or dm dt is what we would be talking about there. The radius of the circle is increasing by 4 feet per hour. That would be r prime is equal to 4, or dr over dt. The volume of a cone, v prime, is decreasing by 2 cubic inches per second, or we would call that dv over dt, right? V prime or dv over dt. Okay, I'm okay with just using prime notation on those, but understand what it's with respect to. Okay, it's with respect to t. So we got to understand that lingo. Okay, so here's what problems are going to look like. Okay, so it's totally up to you if you want to write this down, that's fine, but this can be similar to what homework problems are going to look like. A rectangle is 10 inches by 6 inches, but its sides are changing. Well, think of this. You know what I mean? Right? This rectangle is growing. Right? Now, there are multiple things growing all at the same time. Tell me something that's growing on this thing. The length. What else? The width. What else? The area. What else? The perimeter. Right? They're all changing. So as I drag this, they're all changing. If I go this way, they're all changing, but decreasing, right? Or I could have one where I'm doing this. What's happening there? Width is decreasing, but the length is increasing, right? So the question is, what's the area doing? Is the area increasing or decreasing? I don't know. Maybe it's increasing, maybe it's decreasing, right? So forth. So that's what we're talking about. Write formulas for both the perimeter and the area and how fast each is changing in terms of L and W. So, what's the formula for perimeter? P equals 2L plus 2W. What would be the rate that the perimeter is changing? P prime. We do the derivative. What's the derivative of 2L? Okay, you guys totally missed it. You totally missed the point of what I was just saying a minute ago. Here's what you should have said. You should have shouted this at me. When I said, what's the derivative of 2L, you should have said, Mr. Clark, I can't answer what's the derivative of 2L until you tell me what it's with respect to. Right? You need to know what it's with respect to. Well, actually, I told you when we did that other example, what's it with respect to? We're doing the derivative with respect to, no, t, time. These are all time. These were all changing like per second. The length was changing in inches per second. The width was changing in inches per second. The area would have been changing in square inches per second, right? This is units of time. Now, there's no t in the equation. That's true. So guess what? You're going to tack on an L prime. You're going to do it with every single letter in the problem, unless there's a t, but there's not going to be. If there was a t in the problem, you wouldn't tack on a t prime, because that'd be dt over dt, just like with the x earlier. But any other, the perimeter is changing with respect to time, the L is changing with respect to time, and the W is changing with respect to time. So when we do the derivative, we're doing it with respect to t. So that would be, what we're really saying here is dp over dt is equal to 2, but I'm not going to make you write dl over dt every time. You can just write L prime, but you got to understand why you're doing it. Okay? Just like earlier, we said, what's the derivative of 2y? It's 2y prime. It's a normal derivative, tack on the prime. So implicit differentiation is what we're doing. Plus, what's the derivative of 2w? 2w prime. So we are going to have these problems where they're, what's it called? This is called related rates. The perimeter, the length, and the width are all related, and they're all rates. So we're going to have multiple derivatives in this problem. Okay? What's the formula for area? Length times width. What's the change in the area? The rate of change of the area. That's A prime. What's A prime? Now you're getting it. L prime W plus L, because you're going to have to do the product rule. The derivative of L with respect to T is L prime. W left alone, plus, right. And now we're going to have things to plug into. Okay, so let's move on down to part A. Okay, so moving on to part A, it said, let's say that the length and width are increasing at a rate of 2 inches per second. So we got this situation going on. So the rate, so what does that tell me is 2? No. So L prime is 2 and W prime is 2. So in the problem, they're going to tell you some rates. And those are going to be numbers you get to plug into your equations. So what is the change in the perimeter? The change in the perimeter would be right here, right? P prime would be 2 times 2 plus 2 times 2. That'd be 4 plus 4, which would be 8. And that would be inches per second. Because we'd be doing 2 times 2 inches per second plus 2 times, and I'm not going to be like in physics, I know they make you write out your units on every step of the way. We'll just put our units in at the end, it's fine. Okay, what's the change in area? I should use blue for that. What's this? What's up bad? All right, what's the change in area? That's A prime equals L prime would be 2 W plus L times 2, right? I just put a 2. Oh, we need something for L and W. Oh, wait, right up here. Now, normally it will say, down here it will say, at the instant when the rectangle, because it's growing, right? The rectangle's growing. So the length and width aren't always going to be 10 and 6. They're changing, right? But but they're just telling us the length and width are increasing at this rate all the time. So when the rectangle is 10 inches in length, so that would go there, so that'd be 20, and 6 inches in width, that'd be 12. So this would be 32 square inches per second, right? Now we got to know why that's square inches per second, because the 2's here were inches per second, and then the W, the length and width, are inches. So we got inches per second times inches, so that's square inches per second, okay? But as long as your formulas are right, the units will come out. So you just know it's area, so it's got to be square inches per second, okay? Now, what's the difference over here if we say it's decreasing at a rate? Then L prime is negative 2, and W prime is negative 2. So we got to make sure we read those words correctly and we see that negative that's in there. Okay? All right. So that's what the problems are going to look like. That's how you're going to find these rates. Okay? All right. So let's look at some different situations here. We got some circles. They've got a list. I'm gonna do my own list. Well, let's do one more problem and have you actually write this one out. Okay, so let's say we got a ladder leaning against the wall. Okay, so you guys draw this picture. So for you guys, your picture would look like this. You'd have, let's just say you got a wall and you got this ladder leaning up against the wall, and the ladder is going to fall, right? The ladder is going to be sliding out. The bottom of the ladder is going to slide out, and of course that's going to make the top of the ladder fall down, right? So we have a 6-meter ladder against a wall. The bottom is pulled or pushed at a constant 1/2 meter per second. How fast is the top of the ladder sliding? And let's just pick one of these. How fast is the top of the ladder sliding when it reaches 5 meters up the wall? So when the ladder is 5 meters up the wall. So if we look at this, so you've got this scenario right here. So I can actually slide the ladder, right? This is, I got a little animation here. Okay, so it's sliding out at a constant rate. But now watch the top of the ladder. Watch the top of the ladder. Now, well, first watch the bottom. Do you see how the bottom is constant? See how the bottom is moving at a constant rate? Okay, if you focus your eyes right here, okay, That's just moving at a constant rate. Okay, but now watch the top of the ladder. Is that constant? It gets faster and faster towards down, the farther down, right? So that rate is changing. Okay, but we want to know right when it gets to there, how fast. Okay, all right. So now you wouldn't have all this fanciness here. Your problem, when you work this problem, would look like this. So you would go here and here. You'd say, okay, I got my ladder up against the wall. It's sliding out. It's sliding down. I'm going to label these A, B, and C. Now, how we label it and so forth is the key to these problems. It's the key to getting these problems right. Okay, so the first step is to draw a picture. First steps, and we're going to write this down in a minute. First step is going to be to draw a picture and then label it and write an equation. Okay, so what's our obvious equation for this picture? A squared plus B squared equals C squared. Now, you might also say it could be a trig, like a SOHCAHTOA. It could be, if the problem said something about an angle, how fast is this angle? Because isn't this angle changing too? Right? And this angle is changing? Right? So it could have asked how fast is this angle changing. Then we would have written a SOHCAHTOA equation problem. Okay? So it can vary. It depends what you want. But so maybe I should back up. So now that I've labeled these A, B, and C, let's go back to the problem. What have they told me? Where does the 6 go? So I'm going to write myself a list of things that I know. I know C is 6. Okay? What else do I know right here? They tell me this 1/2. What is that? Now I notice I labeled mine different than up here than they did, but that's okay. No, that's not it. The bottom of the ladder is pulled or pushed at a constant 1/2 meter per second. So what's that 1/2, Emily? B prime, not B. I heard some of you guys say B. No, it's a rate. It's a rate. Now, it's going to be super easy to tell what the rates are, right? I mean, it's meters per second. It's meters per second. That's a rate. That's going to be a prime. That's going to be a prime. That's B prime. Now, is it positive or negative? Positive or negative? 1/2. She says positive. Why is it positive? Because B is doing what? It's a chart. B is increasing, right? B is increasing. So B prime better be positive. Now, what do you suppose about A prime? Doesn't A prime have to be negative, right? Because A is decreasing, right? A is decreasing. Okay, so what about this 5? That's A. Right? What about what they're wanting me to find? What are they wanting me to find? A prime. So I think every problem ought to start with a picture, with labels. You ought to write down the given information that's in the problem with using your labels. That will include some primes and some non-primes. And then you need to write down what are they asking me to find, right? Then you write your equation, right? So if we would have needed a theta, if there was a theta in here that we were looking for, like theta prime, how fast is this angle changing? That'd be theta prime. Then if I had an A and a B and a theta, then I better use tangent, right? I better use tangent, because if I had A and B and theta there, then I need an equation that relates A and B and theta. Well, I would use tangent. But here I need an equation that relates A, B, and C. So I'm going to use theta right there. So you've got to figure out what equation relates the things that you have. Now, here's the next thing. Some of these numbers are constants, and some of them are changing throughout as the ladder is moving. That's key. The ones that are constants you can plug in right away, anytime you want to. The ones that are changing you cannot put in until the very end. That is key. So what about this 6? Is it changing? No. Constant. Okay? What about this B prime? That's constant. So we can put that in any time. Now we don't have a B, we don't have a place to put it right now. What about this 5? That is changing. We cannot plug that 5 in. We cannot plug that 5 in right now in for that A. Can't do it. Because that A is not 5 all the time. So we can't plug that in till the end. Okay? So that's just something you got to understand. Things that aren't changing through the problem, things that are constant the whole time, you can plug those in early or whenever you can. But things that are changing can't get plugged in until the very end. Okay, so now what are we ready to do? We're ready to do the derivative with respect to t. Ready to do the derivative. What's the derivative of a squared? Oh, wait, no. So what can I plug in? I can plug in my 6, can I? So let's plug in my 6. A squared plus b squared equals 36. Okay, let's plug that in. All right, so what's the derivative of a squared? 2a, a prime, plus 2b, b prime, equals 0. Now, let's just pretend, I don't want you to do this because this will confuse you usually, but let's say you forgot to plug the 6 in right away. So over there you had 2c, c prime, right? Now it came time to plug stuff in. So you've now plugged your 6 in for c. What would c prime be? C prime is how fast the ladder length is changing. Is it changing? Then what's c prime? 0. So then you would plug, so as long as you thought that through and said, oh wait, c's not changing, so c prime is 0, then you would get 0 over here anyway, so you'd end up being okay. But usually what happens is people go, oh gosh, I don't know c prime, I don't know what c prime is, and then they get all confused.
Why are you doing like the primes of?
Because we're doing it with respect to t. This is dA dt. It's inches per second, or meters per second. Okay? We're not doing it with respect to x, or we're not doing it with respect to a or b. We're doing it with respect to t. Okay? If it was a, if we're doing the derivative, the reason we didn't do an x prime in those problems, we were doing the derivative with respect to x. And dx over dx is just 1. So x prime is just 1. Right? But we're not doing that here. We're doing the derivative with respect to t. So we have to tack on the a prime. Okay? So 2a prime, 2b b prime equals 0. Now we start plugging stuff in. So we can now plug in for a, we can plug our 5. So we now get 10a prime. Plus 2, what's b? We don't know that yet. What's b prime? 1/2 equals 0. So now we got a problem. We need b. Oh, wait a minute. Now I can plug in a 5 here, and I've got a 6 here. Can I find b? So usually with the given information, we can find any other missing things. So now that I'm to the point where I can plug a 5 in for a, I can now plug a 6 in for c. And so now my Pythagorean theorem, I got 5 squared, plus you guys do that for me on your calculator. So what do we get? That's 6 squared. So 36 minus 25 is what, 11? Square root of 11, what's the square root of 11? Well, let's just put a square root of 11 in there. So I got 2 square root of 11 times a half. Of course, the half and the 2 are going to cancel. So I got 10a prime plus square root of 11 equals 0. So 10a prime equals negative square root of 11. And I got a prime equals negative square root of 11 over 10. Tell me that is a decimal. And it is negative like we thought it should be. What do you got? 3316. And that would be meters per second. So, Emily, the quick answer to your question is, in these problems, you're going to do a prime on every letter that's in the problem. You're going to do a prime on every letter that's in the problem. Because it's always with respect to t. I don't think t will ever be in any of these problems. Okay? All right. And so, let's see if we did it right. And there they go. Negative 0.332. Okay? That's what they got. All right. So that is, so let's write down our steps for our related rates here. Okay? So, first thing we want to do is identify the various amounts and rates that are in the problem. So we identified we identified that we had the ladder against the wall that was sliding, so we drew our picture. I think drawing a picture is pretty good. I think I wrote that in the next step. So we want to identify the various amounts and rates and draw and label a diagram. Now maybe these two go in different order. Maybe you draw the diagram first and then you identify. I mean, these two kind of go together. These steps kind of go together. And I don't know that it's as big a deal to put steps in this as it is the optimization problems, but I think it can be helpful. All right. Now, write an equation that relates those amounts. So we saw that we had a C prime, or no, we saw that we had a C in that problem, we had a B, we had an A, we had an A prime, we were trying to find, we had a B prime that they told us. So I had an A, B, and a C, I needed to relate those. Well, that's Pythagorean theorem. If we'd have had a theta in there, and they wanted to know how fast that angle was changing, then we would have had theta and A and B, and maybe we'd have had a tangent equation we just set up. Okay? And we'd have done that. Okay, so we write an equation that relates those various amounts. Now, I put a little side note there. I said don't plug any values that change in until later. So in that one, when we wrote our equation, we could plug that 6 in right away because the ladder, the hypotenuse, was not changing. Okay, now another problem you're going to run into, and you might even run into it right away, is you got here you got a rest stop on the interstate, or you got an interchange on the interstate. One car takes off and goes north at a certain rate, and another car takes off and goes east at a certain rate. How fast is this distance between them changing? Well, now you got A, B, and C, and all three of those are changing, right? A is changing, B is changing, and C is changing, right? So you wouldn't be able to put any. So if they say, how fast is the distance between them changing when they're 100 miles apart? Well, C would be 100, but you couldn't plug that in right away because that's changing, right? As they're driving, that hypotenuse is changing. So you wouldn't be able to plug that in right away like we did on the ladder problem. Okay. All right. Next one. Differentiate, which means do the derivative with respect to t. And this, Emily, is where you're going to get the primes in all the different parts. Right? Differentiate both sides with respect to t. The nice thing about these problems is you usually do not have to get it down to one variable, right? I mean, that was the big problem in the optimization. We were always doing the derivative with respect to x or whatever our one variable was. We always had to get everything down to one variable. And we had to use that other information to get it down to one variable. Now, there are some times, and we'll do a problem with a cone, where we do have to, it's helpful to get it down to one variable or fewer variables because we don't have enough information to plug into all the different variables. So there are some times where we do want to do that, okay? But a lot of the times we don't have to. All right, substitute then your given value. So now down in step 5, that's when you can put in, you know, all the rest of the values that you're given. Okay? A lot of times you get problems where all the values are changing. So you can't plug in anything until you get down to here. Okay? But in step 3, if you've got some values that are constant the whole time, you can plug those in. And of course, if you have primes that are constant, like we had the 1/2, it was a prime, it was constant, it was a rate. Well, we can't plug it in until down here anyway, because you can't get a prime until you've done your derivative, right? So you plug in your values, and then you just solve, right? And then it says check your answer for the correct sign. In other words, make sure that if, like in ours, A was decreasing, so our A prime better have been a negative answer. And if it wasn't, we'd probably plug something in. Okay? So those are, that's basically the steps that we take there. All right, let's look at one more situation, then I want to go back to an optimization problem. So here would be that's basically the same thing. Okay, let's look at this one. Okay, kind of like this one. So we got a searchlight, and it's spotted this plane. Okay, and it's going to follow the plane. Okay. And then it runs into a storm. Oh, that's not really part of the problem. It's just, oh, then there's, okay, so, look at that. All right, anyway. So, a plane at an altitude of 4,000 feet is flying west at 700 feet per second. Now, the 700 feet per second we're talking about is its airspeed up there, right? That's the rate of change of x. A searchlight under the path tracks it. How fast is the light pivoting when the plane is 1,000 feet to the east? So that would be right here. How fast is the light pivoting? And in this case, we mean how fast is theta changing? Okay, how fast is it pivoting? Is theta. Okay, so we can they labeled this x. We can label this y, right? But is there any need to label that as a y? It's going to be constant, isn't it? So we could, but what do we want? If we've got this, and we've got this, and we've got theta, what equation would we want? Opposite over adjacent. So we would want tangent theta is equal to x over, you could do x over y, but it's okay to plug in the 4,000 right away. Remember, if we've got a number that is never changing in the problem, you can plug it in right away. Okay? All right, so then it might be good to, well, now I said we could do the derivative. I would rather, and that's fine, I would probably write that as 1/4,000, so I wouldn't be tempted to do that as a quotient rule over there. But, so I'm, right? So if you look at our steps we just talked about, draw and label a diagram, which we've done. What information do we have? Maybe we should write that down here. What's this 700? We already got the 4,000 in there. What's the 700? That's x prime. The x prime is 700. Now, is that positive or negative? It would be negative. That's right. It would be negative because it's flying west. Why? Because x is what? What's happening to x as it flies? X is decreasing. Remember the chart. When x is decreasing, x prime would have to be negative. So the x prime is negative 700. What's the 1,000? That's what x is. The x is 1,000, right? So we've got those two values, but we're not going to plug those in now, right? We have to plug those in later. Okay, so let's do our derivative. So now we do the derivative with respect to t. What's the derivative of tangent theta? Secant squared theta, times theta prime, right? Everything's a variable. Theta, x, y, all that stuff, right? We got to tack on a theta prime because that's what we're trying to find. That's what I should have wrote over here. What we're trying to find is theta prime, right? So there's got to be a theta prime in there. Equals, what's the derivative of this? 1/4,000 times x prime, right? Do normal derivative, which means you just have a 1/4,000 and then times an x prime. Well, we know x prime is negative 700. I'm just going to stop right here, but we're going to plug in a negative 700 right there. What we don't know is theta. Now, this is 1 over cosine theta all squared, remember, right? Times theta prime, and over here we're going to have that. Now, what is theta? Well, or what I need is cosine of theta. Well, what's cosine of theta? Cosine is adjacent. So it's not like I actually have to find theta. I got to have cosine of theta. Cosine of theta is adjacent over hypotenuse. Oh, here's my hypotenuse. Can I get that? Don't I have 1,000 and 4,000 here? Right? So 1,000 squared plus 4,000 squared equals my hypotenuse squared. So I can get it, right? So once I get my h, then I can plug that up there, and then I can do inverse cosine of that, right? Or I can solve that equation. I can code whatever that is. 4,000 divided by that, that's cosine theta. I can stick that right in there. I can multiply that over. I got theta prime. Okay? So the rest of that's just simple algebra solving, right? But we need cosine theta. But geez, we got a triangle right here. Cosine theta is adjacent over hypotenuse. We've got 1,000 and 4,000 right there, so we can get the hypotenuse. Okay? And so we can find that. So sometimes you have to find those values. Okay? All right. So follow those steps, set up those equations, do that. All right. So here's what your homework's going to be, and I'm going to help you get started here on one of the problems in the business packet. So we're going to do a little bit of both, okay, on this. So it's the next line on the, it's the next line on there, but it's 4.5 homework. I think it's number 4 and number 7. So we're just kind of getting you started on these related rates. So 4.5 is the related rates, okay. The business packet. And I'm going to post the answers to the business packet, but, you know, be careful in your use of that. Make sure you're working them out, because here's the thing, you guys, I ran through those pretty quick today. I understand on my homework. If you haven't been putting any thought into them, if you haven't been putting some thought into those equations, it was way too fast watching me just go boom, 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 boom through that, I'm sure. To think that you can then go ahead and do a good job on the quiz next week on problems like that. If you haven't been sitting there and trying to work it out and do that stuff, and just sitting here and passively watching me go boom, boom, boom with these already worked out problems, that's not going to be good. You've got to be putting some time into this stuff. All right, so anyway, business packet. You're supposed to finish the circled problems, it says. Finish the business packet, and when I say finish, I mean all the circled ones. Okay? Now, let me help you get a little bit of a start on 15. So if we go to the business packet, yes. Oh, maybe. What do you guys do with business packets? Let me see here. That's weird. Yes, I'll print you. Okay, so on 15, a commodity has a demand function modeled by this. Remember we said that's the price, that's little p. Okay, 100 minus 0.5x squared. I don't know why I just wrote that. And a total cost function modeled by this. What price yields a maximum profit? Okay, so now what was the profit equation? Profit was what? All those terms we had in our notes. Revenue minus cost. Well, they told you the cost equation right there. Now, what was the revenue equation? The revenue equation was the money you bring in. Well, this is the demand function, which means the price per unit. So what was the revenue? It was number of units times the price per unit. So if you sell them for $100 and you sell one of them, your revenue's 100. You sell 2 of them, your revenue's 200. You sell 3 of them, your revenue's 300, right? Your number of units. So our revenue function is X times 100 minus 0.5x squared. That's how you use that. That P, little p, we said yesterday is our demand function, which really means that's our price. Because what's happening is the higher demand, the lower the price. The lower demand, the higher the price, right? So it's an equation. So the price per unit is usually an equation. Okay, so you take your price per unit times number of units. So there's your revenue. And so now you've got your revenue equation, you've got your cost equation, so now you've got your profit equation, right? And so your profit, what price yields maximum profit? So you're going to do P prime, set it equal to 0, blah, 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 right? So you're going to do your revenue minus your cost, okay? And then when the profit is maximized, so once you find that X, then what's the average cost per unit? Well, remember, average cost per unit was your cost equation divided by X. Your cost equation divided by X. So that's how you answer that. Okay, so we haven't talked about that yet, or we haven't done a problem with the demand function little piece, so I just wanted to help you get started on that. Okay, so that's your assignment. Couple of the related rate problems and some stuff in the business. The rest of the circled problems in the business.